There we are. We are back. Back live, I tell you. My goodness. Uh, Feels weird coming back after a 3-day weekend. Yesterday just felt like I don't even know what kind of day it felt like. It was weird. I've told you guys about my buddy Derek and how much of an outlier he is in terms of height. It's just hilarious. But Derek is born and raised in New Jersey. Born and raised in New Jersey. He and I have been friends since middle school. And as you know, he's living in Texas right now. I just got a message from him saying that he's been without power in Texas. He's been without power for a number of hours. Like pretty much he spent the last day and a half with no power in Texas, and it's like 30 degrees, and there's like a foot of snow on the ground, and his heat is off. And it's like, Texas, get your act together. I don't know. No, but Texas got slammed. But anyway, he was directly in the line of fire down there in Austin. Oh, goodness. He'll be fine. He knows what to do. He's tall. He'll know when it stops snowing. Anyway, if you would be so kind as to leave some comments in the live chat, that'd be great for my records. I can take care of that later. And you guys can do that on this wonderful Tuesday morning. I'm only seeing 13 people in the chat so far. Wondering where everyone else is. Possibly, oh no, Ms. Markey, I turned off my alarm the past couple of mornings and now it's hard to put it back on. Well, okay, but, I'm here. Anyway, there they are. There are all those wonderful comments that people are making. There they are. Excellent, excellent, excellent. Okay. Here's my general plan for today. Now, I haven't checked the minor that you guys just took. I haven't checked that yet. I'm going to check that after I teach my classes today. So I won't be able to check that until probably like 10:30. But I will be checking that after I finish teaching for the day, and everything should be updated accordingly. Beyond that, I am going to be either today, at the end of it, depends on how I feel, but I'm either going to be giving you some practice on confidence intervals after what we do today, or I may wait for Thursday to kind of throw that at you. I haven't decided just yet, but I will decide soon enough, Anyway, sorry, I just glanced at the comments and I see Dylan going, woo! And I just imagine that right now he's just like, yeah, and his, and everyone else is like, the level of, anyway, shut up. So I want to continue with what we were doing with confidence intervals. Last time we were at the better setup in my bedroom. Although the one drawback to having the setup in my bedroom is the fact that my kids come in every now and then. Although, my daughter delivered me a chocolate chip pancake the other day. I thought that was fantastic. Just saying. And it really was too. But regardless, we're back here. Now, in a normal year, I have an activity that I like to do in regards to confidence intervals. Unfortunately, a lot of the activities that I have done in the past, I have not been able to do. I haven't been able to put you guys into small groups. I haven't been able to do a lot of the multiple choice challenges that I've wanted to do. I'm going to have to figure something out for that in terms of reviewing with you guys the closer we get to this AP test. But one of the things that I'm really sad about is the fact that I can't do my confidence interval example. Now, even if you guys were here, I can't do that this year. What I wanted to do with this particular ball right here, you can see there's the Earth. Yay, the Earth. Even if you guys were here this particular school year, I would not be able to do what I do. And what we do is this. So I ask the question about what percent of the Earth is covered in water. Now, depending on the resource that you go to, whether it be, a scientist or Google or what have you, scientific journals, textbooks, you'll get a slightly different answer. But the consensus is somewhere between 2/3 and like 75% or some junk like that. And I'm like, okay, well, this Earth that I'm holding right here obviously isn't, completely 100% accurate. But if, 2/3 of the Earth roughly is covered in water, then let's actually put that to the test by attempting to construct a confidence interval. Now, to remind you, the reason why people construct confidence intervals is an attempt to capture the true mean or proportion. It's an attempt to capture the true mean or proportion when you don't actually know what it is. Now, let's just say that I can speculate, like I think I know what percentage of the Earth is covered in water, but we can actually put this to the test. So, in order to construct a confidence interval, you're attempting to capture the true proportion of water on the Earth, or the true proportion of the surface of the Earth that's covered in water, I should say. That should be the more specific statement. But in order to do that, we have to collect a sample. So what I would do is I would say, okay, in a few moments, we're going to take this little, squishy Earth, and we're going to throw it around the room. So you're going to throw it. It's like what you used to do back in elementary school when I have no idea whether or not you guys did this, but I did this a lot when I was in elementary school, where we sat on our desks and we played silent ball, where you had to be like super quiet. I'm pretty sure now it was just the teacher trying to get us to be quiet. But we would sit on the desks and we would have a ball and we'd have to throw it, whatever. And then if you made a mistake, like you threw it weirdly, or if if you were trying to catch it and you dropped it, then you were out and you had to sit back down, and it would keep going until there was like a winner, and that would be silent ball. Lots of opportunities for falling headfirst off your desk. I don't know. Maybe rules in the 90s weren't as strict as they are now, but. So we would play, we wouldn't actually set it on our desks, mind you, it would stand, but we'd throw it back and forth. Can't do it during COVID, but we'd throw it back and forth, around the room. And every time you catch it, that's a trial. And we would count it as a quote unquote success if your pointer finger, and you can see right there, if your pointer finger is over top water. So you'd throw it around the room, and this would be the randomization, where you'd throw it, and of course this thing would rotate in the air, and then you'd catch it. That would be the randomization. Independence of trial to trial. I'd catch it and then be like, look, that's water. And we would count that as a success. And if it was on top of land, your pointer finger, that is, if it was on top of land, we would count that as a failure. So again, going around the room, we'd have to have a minimum of 10 successes and 10 failures. Our sample size would have to be quote unquote large enough. I'd probably aim for like 30 to 40 trials or something like that. Again, randomness, just because the throws, independence can be assumed as a result. Clearly, 30 to 40 throws would be less than 10% of the population of the however many throws we can potentially do. And we would collect that data and we would try to construct a confidence interval with it. Now, I'll tell you, 1 year I had a very amazing sample result. We threw the ball around 30 times, and the results were 15 to 15. 15 landing on water, 15 landing on land. And we constructed the confidence interval from there. Now, the results of that confidence interval and the conclusion that we potentially reached, that was the more interesting part. And that's what I would like to write down with you today. Now, again, like I said, if this were a typical year, we would be in the classroom. We would be actually throwing this ball at each other's head at 7:30 in the morning. But unfortunately, you all at home, probably in your PJs. Here I am in what I slept in. But in the meantime, I'm going to need, if you do not already have them out, I'm going to need those notebooks out and open. I'm going to walk over here. Somebody hit my theme music. So I would imagine like this is like a late night show where once I kind of hit that line and introduce the guests, then I walk over to my desk for the next segment. It's one of those things. Anyway. So there's my duplication. There's that. I am going to get you guys open up on my phone real quick, just so I can have whatchamacallit, the chat open. You're probably seeing it right now through the camera. Let's see. There's AP stat. Let me turn down the volume so nothing's repeating on it. There you go. So I can see your comments and whatnot. That would be fantastic. Oh, you can't see it. The calculator's up right now. I'll clear out the calculator. There we go. And come on, thing, load faster. Haha, there we are. I can see the chat and I can see the number of people there. Fantastic. That's great. Here we go. Okay. Now, I am going to be showing you several things today in regards to calculating these confidence intervals, sample problems that we could potentially do, and the calculator and what it is capable of now that I am back to a calculator that is closer to your guys' speed. I mean, yours is better, clearly, but you do need to know the alternate ways to calculate them on the calculator, but we'll get there. We'll get there. We'll get there. So, boop. Let me bring this up. There we go. And today is the 16th. We're going to call this confidence intervals continued. There we go. Just typically, if you ever see CI, they're referencing confidence intervals. Maybe I should switch to a new marker here. I want to switch to a new marker, which means the old one's going for a ride. It did not make it, but I'm going to pretend like it did. Anyway. So, the question is, what percent of the Earth is covered in water? Question mark. Now, obviously, we could just Google this thing and be done with it. Yay! But that's not the purpose. The purpose is to construct a confidence interval. The purpose of a confidence interval is to attempt to capture the true proportion. We don't have the true proportion. We'll Google it in a little bit, but let's just see what we can do. What in the world happened there? Oh, I see exactly what happened there. So I have my phone open for the chat, and I mentioned what we would do searching for it on the computer. And the second that I said that, my phone picked up the fact that I said, like Google, and it attempted to answer my question. That was hilarious. You can't see that, but that's what it did. Anyway, so we perform an experiment throwing a foam globe around the class, as I described. We perform an experiment throwing a foam globe around the class. There are 30 trials, which is large enough. Now, since we don't know what the true proportion is, we cannot talk about expected successes and expected failures. We can't talk about those because we don't know what the true proportion is. So we can only talk about the samples resulting successes and failures, like the actual experimental in that case. There were 15 successes and 15 failures, which are both greater than 10. And each throw randomizes the result, which, of course, talks about independence. Obviously, we could talk about independence. We could talk about, one person throwing the ball to another person is not going to be the same. We can go into all of those details as well if we wanted to, but we want to try and keep it as concise as possible. If I'm throwing the ball and John Smith over there is throwing the ball, and Jane Doe is throwing the ball, then obviously each of us is throwing it slightly different, which there's independence of throws, thus independence of results, things of that nature. And if we really wanted to get into more detail, we could say that 30 throws is less than 10% of all possible throws, which obviously leads to the independence as well. It's kind of a pain to go through assumptions and conditions, but it is a very good practice for you to do so, especially when we are heading towards hypothesis tests, which one of the aspects of hypothesis testing is stating your assumptions and conditions. So anyway, so knowing all of this, we are going to attempt to construct and interpret. We are going to construct and interpret I don't want 95%. Let's go with a 99%. Yeah. I know we did this last time. I want to do 99. A 99% confidence interval. Yes, that's what we want to do. We want to construct and interpret a 99% confidence interval. So now, the class that I did this with a few years ago, they got 50-50 right on the dot. Now, clearly, 50% of the Earth is not covered in water. 50% of the Earth is not covered in water. It's way more than 50%. But that's just what we got from our sample. So P hat equals 0.5. Awesome. N is equal to 30. Okay. Z star. When you are constructing a confidence interval, in this instance, we're going to need a critical value, a Z star, in order to construct the confidence interval, in order to create that margin of error that we talked about. So we're doing a 99% confidence interval. Now, again, it's not necessary to create this image every single time, but it can be helpful with visualizing the fact that if you're constructing a 99% confidence interval, it's like you're trying to capture the middle 99%, and you're not capturing the outer 1%, which would be split up 0.5 and 0.5. As a result, this right here is the 99.5th percentile. And again, I'll show you the different ways on the calculator that you can get this critical value. We're going to do inverse norm in a moment. But that's the 99.5th percentile. Down here, this would be the 0.5th percentile. But we only really have to worry about the 99.5th percentile. Let's see what it gets us. Calculator. Second vars. Inverse norm. Now, this is the setup that you guys have on your calculator, where you have that tail being left, center, or right. I'm going to show you both left and center. But the area that I'm going to go for, if I'm going to be doing what I just set up on paper, is 0.995. I'm going to keep mu and sigma exactly where they are. I'm going to go down to paste. And by doing it that way, it will spit out my Z critical value, which I'm going to write down as Z star is equal to 2.576. Yeah, 2.576. Now, you could do it that way. You also have another function on here to change left to center. And if you changed it to center, it would spit out two z stars, it would spit out the lower one and the upper one, the negative one and the positive one, but they would be exactly the same. Watch what happens here. Negative 2.576 to positive 2.576. It gives you the exact same z star. You can get it either way. The reason why I need you to know both ways of doing it, I mean, if you're going to be using your Chromebook calculator doing these things, then yeah, you could easily just hit center and knock that thing out. But if for some reason, and again, we've talked about this in the survey because I really don't know exactly what's going to be happening with your AP test, but if you have to take it on paper in school, then you will be issued at that point a sanitized TI-83 calculator, or if you have your own calculator, of course, you could bring that in. But with the TI-83s, they don't have this interface. They don't have the interface of left, right, center. I want you to see one thing before we continue. If I go back to inverse norm real quick, if I typed in a 1, I'll change it to left now, but if I typed in a 1, watch very closely what happens. Because before I put in 0.995 to get the 99.5th percentile, but now I'm going to type in a 1. You know what 1 is in terms of a percentage. 0.995 was 99.5th percentile. This is 1. Watch what happens. I mean, yeah, that makes sense. It counts as it counts it at 100%. And since it counts it at 100%, it's like the highest number that you could possibly go as a z-score. Wanted to show you my calculator here real quick. Watch what happens when I do it on this calculator. If I do 0.995, there's that z star that we talked about. But watch very closely. Inverse norm, 1. Does the same thing. I just need you guys to be aware of that. This thing is nuts. Anyway, back to this. So I typed in, or I wrote down my 2.576. Now I'm ready to construct p hat plus or minus z star times not the standard deviation, because I don't know what my population p is, but my standard error square root of p hat q hat over n. This would give me 0.5 plus or minus 0.2576 times the square root of 0.5 over 30. And that will allow me to construct this confidence interval. Move that up to the top there. There we go. Let's see. I'm going to do my calculator real quick right here. Check this out. I'm just going to calculate the margin of error. 2.576 times the square root of 0.5 times 0.5 over 30. There is my margin of error. Holy crap, that margin of error. Look at that margin of error. That margin of error is ridiculous. 23.5%? Oh my goodness gracious. Hold on. 0.5 plus or minus 0.235. That is not a typo. See, the thing is, that margin of error is so large based on two specific factors. Number one, we only had 30 trials. Yes, 30 trials is sufficient, but it could have been better. Could have been better. The other reason why that margin of error is so large is because of your z-star. We decided to go 99%. We wanted to be 99% confident. Okay. Well, if you're 99% confident, that means that your margin of error is going to be larger, because that's, oh, I put the decimal point in the wrong spot. No, that's correct, but that decimal point should be right there. I should fix that. But because your z-star was a bit larger than what we've done in the past, That caused your margin of error to be larger. That should be right there, 2.576. I think I said it correctly and then wrote it down wrong. Weird. Still got the correct answer. So I would do 0.5 plus 0.235 and 0.5 minus 0.235 to get this constructed 0.265 to 0.735. Now I'm going to interpret that in a moment. But let's just talk about what that means. I am 99% confident that the percent of the Earth that is covered in water is between 26.5% and 73.5%. What the heck? That is such a large window. What the heck? I mentioned last class that there is a certain gold standard that statisticians and pollsters like to use to construct their confidence intervals. And typically it's 95%. 95% may be less confident, but a 95% confidence interval would take this interval and shrink it down a bit. The less confidence you have, the smaller your interval will be, because that is what controls your z-star. But we end up being typically they want to be 95% confident because they want to have a tighter window. See, if I went out with this information and I said, hey, I'm 99% confident that the Earth is covered between 26.5 and 73.5% water, people are going to be like, yeah, duh. But why are you all the way down at 26.5%? Oh, well, it's based on all these calculations and blah, 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 blah. Yeah. This information, though, I mean, it's like a duh type situation. Let me Google this real quick. I said we were going to Google it. I still have to interpret this stuff. But let's just Google how close we were. And that's actually going to inform part of my interpretation. Let's see. Percent of the Earth covered in water. 71%, according to the some government website. I don't know. 71%. Huh. So we pretty much nailed it. Yeah, good for us. Haha. Let's see what happens with the interpretation. So you always have to have a proper interpretation. I am 99% confident that the percent of the Earth covered in water is within the interval 0.265 and 0.735. And according to that government website, we pretty much nailed it. Yeah, 71%. We did it. Good job, people. Woo! Now, of course, if you're going to be presenting data, let's say on like a poll, and I say, I'll go with Joe Biden, for example, because he's our current president. If I said, okay, I took a poll about Joe Biden's, what are they called? Job approval rating. And I'm like, I'm 99% confident that Joe Biden's job approval is between 26.5 and 73.5%. People are going to be like, okay, that doesn't tell us anything. Yeah, but it's somewhere within that range. Yeah, so you're saying the true proportion, which we don't have, you're saying the true proportion could be as low as 26.5 or as high as 73.5? Yeah. Okay, wow. Maybe you want to tighten up that margin of error. There are two specific ways to tighten up that margin of error. You can lower your confidence, which would shrink this z-star. which obviously lowering your lowering your confidence has consequences, which I will talk about in the next statement. Or if you wanted to tighten up that margin of error, you could increase your sample size. Increasing your sample size does shrink that margin of error. So there's multiple ways of going about it. Obviously, the more people that you sample, the more trials that you take, the more time and money that may end up, taking up. Maybe it would be in your best interest to lower your confidence, but let's talk about what that means. We talked about this last time. I'm trying to reiterate this again. What does it mean to be 99% confident? 99% confidence means that in all sample sizes of 30, I want to be specific to the context of the situation. In all sample sizes of 30, I did an experiment with 30. Every classroom in the school did an experiment throwing the ball around with 30. Every school in America did this experiment, but only with a sample size of 30. 99% confident means that in all sample sizes of 30, 99% of constructed confidence intervals would capture the true proportion. 99% confidence means that in all sample sizes of 30, 99% of constructed confidence intervals would capture the true proportion of the percent of Earth covered in water. I'm only talking about sample sizes of 30 because that's what we took. If I wanted to increase the sample size to like 100, then yeah, it would be of sample size of everyone doing a sample of 100. I'm only comparing samples of the same size, same conditions, same assumptions. Every one of those samples most likely would get a slightly different p-hat. A lot of them would get p-hats right where we got them. Some of them would be higher, some of them would be lower. And then they would create their confidence interval. But 99% of those confidence intervals would capture the true proportion, and 1% would not. We are simply hoping that we are within the 99% of confidence intervals that did their job. There is a chance that we are wrong. I mean, thankfully, we're right. I mean, I looked it up. Google said 71%. But there is a chance that we are wrong. We just, as long as we don't know what the true proportion is, there's always a chance that we're wrong. Let me show you something on the calculator. There we go. Go to your calculators. I want to show you something important here. On your calculators, it's going to be the first time we're going to be doing something like this. I need everybody to hit stat. Right there, right in the middle. And I need you to tab over to the word tests. This is the first time we're doing something like this. I need you guys to see this. This is going to be insane. Now, you have a whole bunch of tests here. You have a z-test, a t-test, a two-sample z-test, a two-sample t-test, et cetera, et cetera, et cetera, et cetera. We're not there yet. We're not at the word test yet. But if you go down a little bit farther, you see that it says Z interval and T interval. Yes, those are confidence intervals. However, still, those are not the ones we need. So I'm going to scroll down. There it is. I'm going to scroll down to where it says 1 prop Z int. 1 prop Z int. 1 is referring to the number of samples taken. In this case, it's a 1 sample. Prop, referring to proportion. Z, of course, we used a Z critical value here. And interval. I'm going to hit enter right there. Sweet. Look at this. 1 prop z int is a 1 proportion z interval. X and n are in reference to the number of successes and the number of trials. There we go. C level, hopefully you would recognize at this point, would be confidence level. How confident are you? Well, we want it to be 99% confident. Of course, we were hitting all of the assumptions and conditions along the way. I'm going to calculate. Huzzah! It did it for us. Ms. Markey, why would you not show us this first? Why did we have to calculate it by hand? Because there are 2 specific reasons you need to know how to calculate that by hand. 2 specific reasons. 1, there are going to be some multiple choice questions that don't exactly ask for just the answer. There are going to be some multiple choice questions that may ask specifically what Z star to use or what sample size to use or whatever. And you need to know the formula on how to construct it and how to deconstruct it. So number 1, multiple choice questions. Number 2, there may be some free response questions that have you calculate 1 prop z ints, which is great. You could totally do that. And you can decide, like, here are the assumptions, conditions. I need to construct the interval. I constructed it using the calculator. Yes, that's acceptable. But then a follow-up question may ask a more detailed aspect of the formula, which you have to be ready for. And I'm going to set this up for you. It's going to be great. It's going to be great. First, I want to show you a problem out of the textbook. Now, you don't have to get your textbooks out or ready or anything like that. I have the textbook ready to go. I have a physical copy of the textbook. I just wanted to show this to you so you can see exactly what is going to be expected of you. Boom. Let me zoom in on that. I'm looking at this problem right here. Now, again, I do apologize if it's going to be a little bit bad to read in the live stream. Try to zoom in a little bit more right here. There we go. But I'm going to read this to you, and then I'm going to write down the important information that you need to take out of this. First, vitamin D, whether ingested as a dietary supplement or produced naturally when sunlight falls on the skin, is essentially for strong, healthy bones. The bone disease, rickets, was largely eliminated in England during the 1950s. But now there is a concern that a generation of children more likely to watch TV or play computer games than spend time outdoors is at increased risk. I had to read that in an emotional voice. A recent study of 2,700 children randomly selected from all parts of England found 20% of them deficient in vitamin D. Then it says to find a 98% confidence interval. Which we'll go into the details of, but I just wanted to walk you through this a little bit. Now, first and foremost, 2,700 children randomly selected. Yes, that is large enough. Number 2, they found that 20% of them were deficient in vitamin D. 20% of them. Bring that here. Here we go. 2,700 times 20%. 2,700 times 80%. Good. What I've just checked are making sure that I have more than 10 successes and more than 10 failures. It seems like, well, of course you would. Yeah, but you got to make sure that you make mention of that. You have to make sure that you talk about successes and failures. Randomness is assured because they told us that in that recent study, the children were randomly selected. And because of all of that, because randomly being randomly selected and 2,700 being less than 10% of all the children in England, because you can assume there are more than 27,000 children. Because random selection, because 2,700 is less than 10%, you can assume that vitamin D deficiency is independent from child to child. You have to make sure you nail those assumptions and conditions. You have to. You absolutely have to. Then it says to construct a 98% confidence interval. And then explain carefully what your interval means. That's the interpretation. And then explain what 98% confidence means, which we'll talk about. Now, of course, you could just go straight to your calculator. And I'm just going to show you on my calculator here what it does. Stat, tests, 1 prop z int. What the heck do I type in? They said there were 2,700 kids. Which is the value of n. And it was 98%. But what the heck do I put in for x? This is what you have to know about your calculator. It doesn't matter if you're using the 83 or the special calculator that you guys have on your computers. You have to know what x is. X is the number of observed successes. In this case, look what I just typed in there. Now, here's something that you have to know. Something that you absolutely have to know. First of all, I'm going to hit enter. And when I hit enter, that x is going to automatically calculate. Watch this. There it is. It automatically calculated it. That was nice. But sometimes that x value will end up being a decimal. And if you attempt to calculate with that x value being a decimal, there will be an error on the calculator. Your calculator needs that x value to be a whole number. So at that point, you have two options. Number one, you could alter that x value to be a whole number, meaning just kind of round to the nearest whole number. Sometimes it's a great idea. Sometimes it's not a great idea. Your other option is to calculate this thing by hand, which we're about to do. So let's knock that out. Now, I've already talked about my assumptions and conditions, so I'm not going to go through that again. But let's just write down some pertinent information about this problem. This problem is from page 490 in your textbook, and it's number 24, just for the sake of reference. Said there was a sample size of 2,700. They found a p-hat of 20%, and they want 98% confidence. Again, if you're 98% confident, that means that you're not capturing the outer 2%, which is broken up as 1%, 1%, which means that this, as a result of that 1% being to the right, is the 99th percentile. It's the 99th percentile. Oh, weirdness. Anyway, knowing that, I'm going to do an inverse norm 0.99. Here we go. Inverse norm 0.99. Come on, you. 9. I'm going to keep it left. Paste. There we go. There's my Z star. So my Z star should be 2.326. I don't know why I want to go that far, but okay. All right. 0.20 plus or minus 2.326 square root 0.20, 0.80 over 2,700. Now, yes, they went down to 98% confidence. They went down to 98% confidence, which is not that bad. But they had 2,700 trials, which means that our margin of error is going to be a bit smaller. In fact, sometimes these problems are just going to ask you what is the margin of error, not what the confidence interval is, but what is the margin of error. Now, there is a way of doing that on the calculator, which I'll show you, but you could just calculate it here by hand. Let me see what that gets me. 2.326. Come here, you. 2.326 times the square root of 0.2 times 0.8 divided by 2,700. Margin of error, 0.018. It's a 1.8% margin of error. 1.8% margin of error. All right. There we go. Which creates a confidence interval of 0.182 to 0.218. This is the interpretation part, we are 98% confident that the true proportion, now again, I'm going to put this into the context of the problem. You need to put this into the context of the problem. We are 98% confident that the true proportion of kids in England with vitamin D deficiencies is between 18.2 and 21.8%. You need to put it in the context of the problem. We are 98% confident that kids in England suffering from vitamin D deficiencies is between 18.2 and 21.8%. That's explaining carefully what the interval means. But now, what does the 98% mean? The 98% means that I am, well, not that I am, but I'm going back and forth to the other one, but in 98% of confidence intervals constructed from the same sample size, I'm stating in a slightly different way, but let me repeat that. In 98% of confidence intervals constructed using the same sample size, they would capture the true proportion. Or I would say, in sample sizes of similar size that construct confidence intervals, 98% of them would capture the true proportion and 2% would not. I'm just simply hoping I'm one of the 98%. There's a good chance that I'm part of the 98%. I'm 98% confident, but that's what it comes down to. Now, let me iterate one very important thing here, and I'm going to put a star in order to indicate how important this is. When I say I'm 98% confident, that does not indicate a 98% chance. That does not indicate a 98% chance. Move that over a tiny bit. See it a little bit better? When I say I'm 98% confident, that does not indicate a 98% chance. It doesn't. I want to be very clear about this. This is not about probability in this exact moment. This is not about probability. When you say you're 98% confident, it means that 98% of the confidence intervals of similar sample size would capture the true proportion and 2% would not. That does not mean you have a 98% chance. It doesn't. Do not conflate the two. There is possibility in the future of calculating the probability of such an event happening, calculating the probability of you getting such sample results. But this is not that. To be very clear, this is not that. Okay. One more thing that I want to talk about before we go for the day. One more thing that I want to talk about. I want to set up a scenario. I want to, I want to conduct a sample of the percent of people who are left-handed. I want to conduct a sample of the percent of people who are left-handed. And then construct a confidence interval with a margin of error less than, let's say less than 3%, with 95% confidence. Now here's the question. What should my sample size be? What should my sample size be? Now, we may not finish this question today. But I want to talk very deeply about what this question entails. But let me repeat the question. I want to conduct a sample of the percent of people who are left-handed. And then I want to construct a confidence interval that has a margin of error less than 3%. I need it to be less than 3%. Why? I don't know. Just because I want it to be less than 3%. I just want it to be less than 3%. Less than or equal to, whatever. I don't know. Probably less than. But I want to be 95% confident. You know, I can set my confidence level. I want my confidence level to be 95%, which is the gold standard. Okay. What should my sample size be? Now, when you construct a confidence interval, you typically have a p-hat. Here's the thing. I haven't conducted the sample yet. I don't have a p-hat. I want to conduct a sample. I haven't done it yet. I don't have a p-hat. But I still want my margin of error to be less than 3%. So what should my sample size be? This is kind of like a chicken or the egg situation here. I can set up the formula, but I need to know what p-hat is. But I can't have p-hat until I actually conduct the sample. But I can't conduct the sample without my sample size. But the question is, what should my sample size be? What do I do? Where does it come from? That's the noise I make. Check this out. First of all, your Z star is based on a 95% confidence interval, which means I'm going to do inverse norm 0.975 to get a Z star at 1.96. That should be my Z star. My margin of error needs to be my margin of error needs to be less than 3%. That is the calculation that I need to figure out. Look what I have up there. I need my margin of error, which is Z star times the square root of p hat q hat over n, Z star times my standard error. I need that to be less than 3%. I know that my Z star is 1.96. That's based on 95% confidence. But I have no idea what p hat and q hat are. In this scenario, you can assume one very key important thing. In this scenario, where you do not even have a p hat, you can assume a p hat q hat of 0.5, 0.5. Mr. Markey, why? Why 0.5 and 0.5? If you put in 0.5 and 0.5 for your p hat and your q hat, it will maximize the top of this fraction. And if it maximizes the top of this fraction, then solving this for n will allow you to get the largest possible sample size that you need to get. It is better to have a larger sample size than not. If you want to get under 3%, then you need to figure out what your sample size should be. It's like, okay, well, I don't want it to be, too big. I can't just have like 50,000 people in my sample because that would take too much time and money. So I have to have something a bit more reasonable. Put 0.5 and 0.5 here. If you don't know what p hat and q hat are, it will maximize the top of that fraction and allow you to get the optimal sample size. 0.5 times 0.5 is 0.25. If you have any type of p and q, 0.25 is the largest value that you could have. I mean, it could be like, 0.1 and 0.99. Or I'm sorry, not 0.1 and 0.99, like 0.1 and 0.9 or some junk like that. And it's just like, okay, well, those multiple together is like 0.09. I know, it's a lot smaller. You want to maximize that, you got to do 0.5 times 0.5. Now, I'm going to set this up, but I'm not going to solve it today because I'm a little out of time right now. But you can, if you want to show off those algebra skills. And yes, this is nothing more than an algebraic problem. You basically just have to solve that bottom inequality for n. And if you solve that bottom inequality for n, you will figure out what your sample size should be. Of course, most likely you'll end up with a decimal, and you should round up, because by rounding up, you will guarantee that the sample size will be less than 3% rather than greater than. We're going to pick up with this next time. I'll show you what the correct answer is. I will have some sample problems for you, and we will get this thing moving. The time is about to end in a few seconds, so everyone should have a great morning. There's no bell. There's the bell. I was off by half a second, and now I'm sad. Now I'm going to go sit down, drink my coffee. Anyway, I'm going to sign off. Thank you guys for being here this morning. If you haven't left a comment in the chat, please make sure that you have done so, because I'm about to sign off because I got to get to my next class. Have a wonderful day, and we'll see you next time.